Imagine waking up every morning and watching the sun rise in the east, travel slowly across the sky, and then sink below the horizon in the west. Every single day, without fail. Now, ask yourself honestly, what does that look like to you? It looks like the sun is moving, right? It looks like the sun is orbiting us. And you know what? You wouldn't be wrong for thinking that. In fact, some of the greatest minds in human history, brilliant astronomers, mathematicians, and philosophers, believed exactly the same thing for nearly 2,000 years. But here's the shocking part. They were completely, utterly wrong. And the person who finally dared to say so, he was a quiet Polish priest who spent his nights staring at the stars and his days afraid to publish his discovery because he knew the world wasn't ready to hear it. His name was Nicolaus Copernicus, and in 1543, he changed our understanding of the universe forever. Let's go back, way back, to ancient Greece. Picture this. You're a philosopher standing on a hilltop around 400 BC. Every night, you look up at the sky. The stars rotate overhead in perfect, predictable circles. The sun rises and sets, the moon moves, and you're standing still on solid ground beneath your feet. What would you conclude? Almost every ancient thinker concluded the same thing. Earth is the center of everything. The sun, the moon, the stars, the planets, they all orbit us. This idea even had a name. It was called the geocentric model, from the Greek word geo, meaning earth. And honestly, it made total sense at the time. Think about it like this. If you're sitting inside a moving train and you look out the window, the trees appear to be flying past you, but you feel completely still. Your brain tells you you're not moving. The world outside is. Ancient humans experienced the cosmos the same way. They felt no movement beneath their feet, so logically, Earth must be standing still while everything else spins around it. By around 150 AD, a Greek-Egyptian astronomer named Claudius Ptolemy had built an extraordinarily detailed mathematical system to explain this geocentric universe. His model could predict where planets would appear in the sky weeks or even months in advance, and it worked. It was good enough that people used it for navigation, farming, and religious calendars for over 1,000 years. For 14 centuries, nobody seriously questioned it. Until one man did. Nicolaus Copernicus was born in 1473 in Royal Prussia, what is now Poland. He was a man of many talents. A physician, a mathematician, a church official, and above all else, an obsessive skywatcher. As Copernicus studied the movements of planets across the night sky, he noticed something deeply troubling about the Ptolemaic geocentric model. The planets didn't move smoothly. Mars, for example, would sometimes appear to slow down, stop, and then move backwards across the sky before continuing forward again. Astronomers called this retrograde motion, and they had all sorts of complex mathematical tricks to explain it within the geocentric model, including a bizarre concept called epicycles, where planets were imagined to move in small circles while also moving in larger circles around Earth. It was like describing a person walking forward by saying they're actually doing tiny backflips while simultaneously riding a carousel. Technically, it worked mathematically, but it was messy, complicated, inelegant. And Copernicus couldn't accept it. He had a feeling, a deep, almost artistic conviction that the universe should operate on simpler, more beautiful principles. So he started from scratch. What if, he asked himself, the sun was not orbiting Earth? What if Earth was orbiting the sun? He began rebuilding his model of the solar system with the sun at the center. This is what we now call the heliocentric model, from the Greek word helios, meaning sun. And something remarkable happened. When he placed the sun at the center, that strange backwards motion of Mars, it disappeared.
Suddenly, it wasn't Mars moving backward at all. It was just Earth catching up and overtaking Mars as both planets moved around the sun at different speeds. Like when you're on a highway and you pass a slower car. From your perspective, that car appears to briefly move backwards, even though it's still driving forward. The retrograde motion wasn't real. It was an illusion caused by our own movement. Everything clicked.
Copernicus spent decades refining his heliocentric model, and in 1543, the same year he died, his masterwork was finally published, De Revolutionibus Orbium Coelestium, which translates to On the Revolutions of the Celestial Spheres. In this book, he laid out 6 bold propositions that overturned everything. 1. The Earth is not the center of the universe. 2. The Sun is the center of the solar system. 3. Earth rotates on its own axis once every 24 hours, which is why the stars appear to move overhead at night. 4. Earth completes one full orbit around the Sun every year. 5. The other planets also orbit the Sun, each at different distances and different speeds. 6. The closer a planet is to the Sun, the faster it moves. Now, Copernicus's model wasn't perfect. He still believed the planets moved in perfect circles, which they don't, and his predictions weren't quite as accurate as Ptolemy's in certain cases. That improvement would come later from Johannes Kepler, who discovered that planetary orbits are actually ellipses, not circles. And then came Galileo Galilei. In 1609, Galileo pointed a newly invented telescope at the sky and made a series of breathtaking observations. He discovered 4 moons orbiting Jupiter, proving for the first time that not everything orbited Earth. He observed that Venus had phases, just like our moon, which could only be explained if Venus was orbiting the Sun, not Earth. The evidence was stacking up, piece by piece, observation by observation. Finally, in 1687, Isaac Newton provided the physical explanation for why the heliocentric model worked. His law of universal gravitation showed that the Sun, being incomparably more massive than any planet, exerts an enormous gravitational pull.
Here's where it gets truly mind-bending. The Sun isn't just slightly larger than Earth. It is incomprehensibly larger. If the Sun were the size of a basketball, Earth would be roughly the size of a peppercorn. And you'd have to place that peppercorn about 26 meters, nearly 85 feet away from the basketball to represent the actual distance between us. And yet, for 2,000 years, humans looked at that basketball-sized object hanging in the sky and said, it must be revolving around the peppercorn. Why? Because we trusted our senses over our calculations. Because what feels true and what is true are not always the same thing. This is one of the most profound lessons in the history of science. Our intuition is not always a reliable guide to reality. The Earth feels still, but it's moving through space at roughly 107,000 kilometers per hour. That's nearly 30 kilometers every single second as it orbits the Sun. You feel nothing. You sense nothing. But you are hurtling through space right now at a speed that would circle the entire Earth in about 22 minutes. Copernicus didn't just shift the Sun to the center of the solar system. He shifted humanity's entire sense of itself. He knocked us off the cosmic throne we had placed ourselves on and revealed that we are passengers on a small, spinning rock, orbiting an average star, somewhere in the outer arm of one galaxy among hundreds of billions. That's humbling, and it's magnificent. You might be thinking, okay, this is fascinating history, but does it actually matter today? Absolutely. Everything. Every GPS satellite orbiting our planet uses calculations based on the heliocentric model and Newtonian gravity. When NASA launches a spacecraft to Mars, mission controllers must calculate where Mars will be months from now, based on the precise understanding that both Earth and Mars are orbiting the Sun at known speeds and trajectories. The Voyager 1 spacecraft, launched in 1977, is now over 23 billion kilometers from Earth. It's still sending signals back.
Scientists can predict exactly where it is at any given moment because of the mathematical framework that Copernicus, Kepler, Galileo, and Newton built together over 150 years. Even the timing of your smartphone depends on atomic clocks on GPS satellites that must account for the movement of Earth around the sun. The Copernican revolution didn't just change astronomy, it changed science itself. It taught us that we must follow the evidence, even when the evidence is shocking, even when it contradicts what our eyes tell us, even when it challenges our most deeply held beliefs about our most deeply dedicated beliefs about our place in the universe. It gave birth to the scientific method: observe, hypothesize, test, revise, and question everything, including your own assumptions.
In 1543, a dying man in a small Polish town received the first printed copy of his life's work just days before he passed away. He may have been too weak to fully read it himself. He never knew how completely it would change the world. Nicolaus Copernicus didn't have a telescope. He didn't have a computer. He didn't have satellites or space probes or any of the tools we take for granted today. He had nothing but math, patience, and an unshakable belief that the universe, however inconvenient and humbling its truths might be, deserved to be understood honestly. He looked up at the same sky that every human before him had seen and asked a different question. Not, what does this look like, but what does this mean? And that single shift from appearance to reality is what science is all about. So the next time you step outside and watch the sunrise, remember, you're not watching the sun move. You're feeling the Earth turn. You're a passenger on a rotating planet, racing around a star in a universe so vast and so strange that our greatest challenge, even now, is simply letting go of what feels obvious and chasing what is actually true. That is the legacy of Copernicus. And the question he left for all of us is still alive today. What else do we think we know that we might have completely backwards?